Hi, everybody. I'm Layla. Thanks a lot for having me here today. I'm with Maluuba. We're based in Montreal, and we just got acquired by Microsoft about a month ago, so now we're part of Microsoft Research. And today I'm going to talk about teaching AI to make decisions and communicate. So how do I go to the next slide? Okay. So first, I'd like to tell you a bit about our vision. We want to create artificial intelligent agents by creating literate machines. So we're focusing on language. And there are two reasons for this. The first reason is that if you want to make an artificial intelligent agent that is going to be used by a majority of people, you need to make it use natural language because it's the favorite medium of communication that we use. It's the medium that I'm using right now, and it's the one that is the most accessible to everyone. And it's what we want to do in Maluuba and at Microsoft more globally. We want to democratize AI, so it's very important for us to make machines that can talk. And the second reason is that language is very intricate with human intelligence because we use language to express what we know, but we also acquire new knowledge through language, and language kind of shapes us as we use it. So it's very fascinating to study how to use language and how to make machines understand and use language, because at the same time we also understand more about how we use it. So in order to study language, we have kind of divided the problem in three main areas that are very complementary. The first one is machine reading comprehension. So this is about trying to understand documents and, for instance, being able to answer questions about a document, because that's how we measure our understanding capabilities at school. You know, you read some document and then you have questions to answer about it. So that's one area that we're studying. Another area is advanced conversational systems. So, you know, once you have read the documents, you need to be able to talk about the documents. You need to be able to talk about it with human beings. And so we are working on dialogue systems that are able to do those kind of things. And the third area is reinforcement learning, and I'm really glad that we had a great talk about reinforcement learning by Ben Lau and deep reinforcement learning. So I'm going to talk a bit about how we use reinforcement learning. It's really a core skill that we're using to study language. So this is the overview of the talk that I'm going to give today. I'm going to talk about some of the works that we've been doing at the lab. So first, I'll give you a more concrete example of what we're trying to achieve and what we expect. Then I'll speak about learning to learn, learning to perceive, and learning to communicate. So what do we expect? That's kind of the agent that we really want to build in the long term. So this is an example of an ideal dialogue that you would have with this agent. So you have an appointment, and you want to know when this appointment is. So you ask him, when is my appointment with Mark? And then the agent comes back with the information, and it tells you, you have a meeting with Mark Villeneuve tomorrow at 10 a.m. So here I say learning to communicate, because what the agent did here is that it went to my calendar and it got the information, but then it didn't just drop the calendar item to me. It expressed what it found in the calendar in natural language, so it can communicate like a human being. Then I ask it, okay, where is this meeting? And it tells me it's Starbucks on Maisonneuve and Montaigne. Those are streets in Montreal. And it also adds the fact that I should leave the office at 9:40 to make it there at 10 a.m. So here I say learning to learn, because the only thing that I asked the agent here was, where is the meeting? But it gave me more information. It told me when I should leave. And it probably learned that because every time I ask it where a meeting is, I always follow up with the question, okay, when should I leave to be there on time? And so it learned this behavior, and now it's proactive, and it just does it without my bothering to ask it. So then I ask it, okay, is it the same Starbucks when I had another meeting? And it says yes, so it has memory, can retrieve information from the past. Okay, so then I ask it, okay, great, so do you know what Mark's been up to lately? And here It went to get information on the internet, so it probably read an article from MIT Tech Review here, and it tells me, okay, yeah, so what Mark has been up to lately is that his company is going to start commercializing affordable 3D printers. So that's learning to perceive, because it went to get the information, it read documents in an unstructured format because it's just free text, and then it was able to render this information to me. So that's exactly what we're trying to build at Maluuba, and so I'm going to deep dive in all three aspects: learning to learn, learning to perceive, and learning to communicate in this order. So first, learning to learn. One thing that we're working on right now, and that's linked to how human beings learn new tasks, is an efficient way to decompose tasks into subtasks. And human beings are really, really good at this because we're really good at saving energy. And here I take the example of driving. When you learn to drive, when you have your first driving lessons, it's usually very exhausting because you have to learn so many new things, and you have to identify new situations and be able to match those situations to actions. But with time, what your brain is going to do is that it's going to decompose the task of learning into subtasks that it can perform without even being consciously aware of it. So for instance, you're going to be perfectly able of starting your car on a flat road. And you're going to be able of doing this without even thinking about it, because it's always the same thing that you need to do. It never changes. Doesn't matter about the road. If it's flat, you just know how to start your car. You don't need to think about it. Another example is just braking in time for a red light. You don't really need to think about it. It becomes kind of a reflex. You just do it. But then there are some harder tasks, like starting your car on a hill, and then here you need to give it a bit more thinking, but with time and with practice, again, you will learn to do it without thinking about it. And why you do that, it's so that when you're in an expected situation, so for instance, if you have a kid who just comes on the road, here you have enough energy. You're not exhausted from thinking about all the other subtasks. You have enough energy and consciousness free to just be able to react to this situation that requires you to react. And so we're really good at decomposing tasks into those small subtasks that we can just perform and transfer from situation to situation. So for every road, you know how to start your car. You don't need to think about a specific behavior for every different road. And we thought of a framework that is inspired from this. So Ben already presented the reinforcement learning setting. So in the reinforcement learning setting, you have an agent that performs actions in an environment, and based on those actions, the agent receives rewards or penalties. And the goal of the agent is to learn for each state of the environment the action that will maximize the expected sum of rewards starting from the state. So that's the classical setting. Our setting, called the separation of concerns, is a way of having several agents that will each agent is going to be responsible for one subtasks. So here we decompose the global task into several subtasks that are each handled by one specific RL agent. And each agent will have its own objective to fulfill. So it will have its own reward function. So for instance, one agent will learn to start the car, and its reward will be, okay, did you start the car successfully or not? Another agent will learn to brake, and its reward will be, did you brake in time? Did you brake in time for the red light? So that's how we're going to decompose the task of driving, for instance, into subtasks. So an example of application where this kind of decomposition is useful is Pac-Man. So in Pac-Man, you have to collect those little, we call them fruits, but I'm not really sure what they are. So you need to collect those little dots that we call fruits, and you also need to stay away from ghosts. So you have those two tasks that you need to perform at the same time. And we looked at how classical deep RL methods such as DQN that Ben Lau just presented performed on this task, and they didn't perform really well. So here the scores that you see are normalized by human performance. So human performance is at 100%, a completely random agent is at 0%, and here you can see that the best that we could do was approximately 14%. So we thought of decomposing this task into several subtasks. If you look at the task of collecting all the fruits, the problem here is if you have n fruits, your state space is going to grow exponentially with the number of fruits. If you have n different fruits, it's going to be a hard problem. It's an NP-complete problem to collect all the fruits. But if you decompose this task of collecting all the fruit into n subtasks with n different agents, and each agent is responsible for one fruit, then you reduce the state space dramatically. It becomes linear in the number of fruits. So that's what we did. And we worked on a simplified Pac-Man that we call Pac-Boy. And here you have, so it's a grid that looks like Pac-Man. The white square is the Pac-Boy, the red ones are the ghosts, and the purple ones are the fruits. And in our setting, the reward was giving +1 to the agent for eating a fruit and -10 for every time it would collide with a ghost. And the episode ended after the agent collected all the fruits, or after 300 time steps. We put a maximum number of steps. And here the state space was approximately 1,000 states. Sorry, I'm going back. So the configuration was this one. We had one agent per fruit, one agent per ghost. And so the blue agents at the bottom here are the fruit agents, and the two red agents are the ghost agents. And then we had an aggregator that was taking the Q values for each of these agents and then making the final decision based on what those agents were advising. So in total, we had 75 fruit agents. Each of them had 76 states, and 2 ghost agents with 76 times 76 states. So here I have a demo of our setting SOC versus DQN. So they're going to start it. So here, if you look at the DQN agent, it has a very conservative behavior. Here it's just hiding from the ghost. It's very scared of the ghost, so it just decides to stay here. And then it just continues at some point. Yeah, he just hides in the corner. He kind of plays dead, doesn't want to hit the ghost, so it ends up not collecting all the fruits and just, kind of getting stuck there. Now, if you look at the separation of concerns agents, so the one with agents for each fruit and for avoiding the ghost, we see a different behavior. So here the agent is less conservative. It implements a better trade-off between avoiding the ghost and collecting all the fruits, and it actually collects all the fruit very quickly. That's an interesting demo, I think. And if we look at the results in terms of learning curves, so here we see the separation of concern agent, which is the red curve. It reaches a near optimal behavior. It gets really closer to the upper bound of 40 very quickly after only about 10 epochs versus the DQN agent that never reaches an optimal behavior because we just saw it doesn't get all the fruits. It's very conservative, and so it converges to a very suboptimal behavior. And if we look in terms of average steps, so that's on the right, we see that the separation of concerns agent finishes the episodes very quickly, so after less than 100, after approximately 100 steps, whereas the other agents take much more steps or never finish. They're only finished after the max number of steps, which was 300 in this case. So that's the separation of concerns setting, and it's the first step, we believe, in modeling the way that the brain kind of decomposes the tasks into subtasks and has this kind of very efficient way of decomposing tasks that we have to do every day. So that's one step, because we kind of handcrafted the decomposition, but then in the future we want to learn this decomposition and make it so that we emulate the decision making in the brain more efficiently. So now I'm going to talk about another stream of research, which is learning to perceive. So if we just do a bit of history here, the first living creatures, they could only perceive the world through very coarse senses. So basically they were only able to react. So if there was light, they would be able to just go away from it, but that's it. They didn't have any capability of planning or anything. They were only able to react. Then with the development of nervous systems, living creatures were able to kind of combine sensory inputs together and have a better representation of the world. And finally, we, as modern living creatures, were able to focus. So because the thing is, we have thousands of sensors. If you look at the nerves, the eyes, the ears, the tongue, everything, we have thousands of sensors. But we need to be able to focus on some of them, given what we're trying to do. So if you put your hand close to fire, you need to focus on those nerves and ignore all the rest, to just remove your hand from the fire. And so you have a huge search space, and you need to be able to extract the salient features in order to accomplish the task that you're trying to accomplish. And that's another thing that we're really good at after millions of years of evolution as human beings. And that's also something we're trying to work on. So in order to have a similar problem where you have a big state space and you just want to focus on, to learn where to look at, basically, to learn where to focus in order to accomplish a task, we designed a few games. Basically, the first one is Battleship. So in this game, you need to sink the enemy ship very quickly, so you need to know where to look at in order to make it as efficient as possible. So here in this configuration, your agent should learn that it needs to look underneath the boat that's not finished here, because the other parts of the state space are not relevant. There's also a hangman, where you need to learn which letters to try out based on the letters that you already have. And there's block word, on which I will spend a bit more time. So block world is this setting where you have simple shapes, and you need to answer a question about the image. So here the question is the red sphere above the red cross? And here you have no red sphere, so the answer is no. So in the first line you have the environment, so that's the image. But on the second line you have what the agent thinks the environment looks like. On the third line you have the decisions that the agent makes at each step. And on the fourth line, you have the observations. So at the beginning, if you look at the observations line, the agent hasn't seen anything, and its actions consist of peeking at some clusters of pixels. So the first action it makes is looking at the green diamond, and it just looks at some of the pixels that constitute the green diamond. And so it updates its belief. So that's on the second line. And it starts understanding that there's a green diamond. And so if you look at the last line, that's the model's answer belief. So the lighter it is, the more the agent thinks that the answer is yes. So at the beginning, the system doesn't really know. So it doesn't really know if there's a red sphere above the red cross. It doesn't really know enough about the environment. But as it looks, it starts looking at the red square. And then, no, it starts looking at the red cross if you look at the model's world belief. And then it sees a red cross, so it thinks, okay, so the probability that there's a red sphere above it is higher because there's actually a red cross on this image. So then it becomes lighter. But after a while, it sees that it's actually a red square and not a red sphere. And so its model answer belief at the end is it's very certain that the answer is no to this question. And so here the agent learned where to look at very, very efficiently, because if you look at the observations line at the end, it only looked at a few pixels of the image to be very sure that the answer to the question was no. So it was able to focus on what was important to answer the question. So I'm not going to spend too much time on this, but that's a model that we've been using to do this. So that model we used for labeling. So imagine you have, we actually did it on an artificially generated data set of flowers. We generated it ourselves, and it was just flowers with different stems, shapes, shapes of leaves, etc. And here, the agent learned what flowers it needed to look at to be able to label a new flower efficiently. So if it had flowers, they all had a class. We just made classes. Okay, those flowers have green stems, for instance. That was a class, etc. And then the model had to learn to look at the right flowers in order to be able to label a new flower that it hasn't seen before. And so that's what this model does. So it just picks up items to label, and then based on those, it learns how to label an item that it has never seen before very efficiently. And we trained this model end-to-end with reinforcement learning, and the reward function was based on the accuracy of the model's labeling. And the last the last topic that is very important is learning to communicate. So once you've learned to learn, once you've learned to accomplish tasks and where to look at in the environment to be able to accomplish those tasks, so once you've learned to perceive, you need to be able to communicate your findings to a human being. So that's learning to communicate. And so when we communicate, it's not always easy, because language is the most complete tool that we have, but it's also not so precise, because very often when someone says something, the person listening is going to get another meaning that was intended. There's a lot of misunderstandings happening all the time. And there's actually a French philosopher that is named Brice Parent, who was very obsessed about language. He was even nicknamed the Sherlock Holmes of language. He just studied this all his life. And at some point, he made a really good observation. He said that the most precise way to communicate with someone is to actually give him orders. Because when you give an order, there's no room for misunderstanding. If you define your order precisely enough, you just tell the other person what the word should mean. Basically, you relate it to an action, and so it's a very, very efficient way of communicating. And we're kind of following this in our research, because before we go towards more sophisticated uses of language, before we study sarcasm and those irony, those kind of things, we're just studying right now orders. So if you talk to a machine, in order to make it achieve something for you, to make it book a restaurant for you, or book an airplane ticket for you, so that there's not so much room for misunderstanding in this setting. So that's what we study. And so how do we build a dialogue system in practice? So first we have what we call natural language understanding. So it takes the user utterance, for instance here, I want to go to Rio, and then it extracts what we call the dialogue act. So the dialogue act is kind of an abstract summary of the utterance. So here it's inform, because the user is informing you that he wants to go to Rio. And it also extracts the named entities. So here the named entity is the city and it's Rio. Then this is passed to what we call the state tracker. The state tracker will keep track of what the user is searching for throughout the dialogue. So here, it already knew, because the user already told it that he had a budget of $2,000. And so he adds to this budget that the city that the user wants to go to is Rio. So the new user goal is city equal Rio and budget equal $2,000. And then the state tracker is also communicating with a database to retrieve items. So here it will retrieve a trip to Rio for $2,000. And here he has a Hilton for $1,950. And then it will pass all this information to the dialogue manager. And the dialogue manager is responsible for deciding what to say next to the user. So here it will say, okay, that looks good. I'm going to propose this hotel to the user. And then we have natural language generation that takes this decision and then makes it into a sentence, a natural language sentence. So here you can book the Hilton for $1,950. So that's how we build a dialogue system in practice. And what we've decided to do is to go one step further and model memory. Because those kind of dialogue systems, they work really well if you know what you want. If you know you want to go to Rio and you know your budget and you just want to have a hotel, then that's perfect. But if you're not so sure, you maybe want to go to Rio, maybe you want to go to Cuba, you're not really sure, you want to kind of explore, then you need to have a dialogue system that can keep track of different things. You need to have a dialogue system that can keep track of Rio, of Cuba, and then you can compare both. And this was not possible with the architecture that I just presented. So in order to study architectures that can do that, we collected a data set called frames, and that's going to be publicly available very soon. And so our idea here was to study memory. So here, if we look at the end, the user says, okay, I want to go to Curitiba. And the user talked about Curitiba way back at the beginning of the dialogue, so the dialogue system would need to retrieve that information, but actually, it's actually there that the dialogue system needs to look at, because that's the hotel that the dialogue system proposed in Curitiba. So that's the information that the dialogue system needs to retrieve at the end. And there's also other information that happened in the dialogue because the user also explored an option in Columbus. And so the dialogue system needed to know, what to remember, where to look at in the dialogue in order to retrieve the hotel in Curitiba that the user wanted. So that's an overview of the data set. We collected about 1,400 dialogues. Each dialogue had about 15 turns in average. You can see it in the dialogue length distribution. So that's a total of 20,000 dialogue turns. And we formalized the idea of memory in a task that we call frame tracking. So I presented state tracking where you were keeping track of the user goal throughout the dialogue. But what happened with state tracking is that if the user changed the value, if the user first said, I want to go to Curitiba, but then said, okay, what about if I go to Columbus? Then you would completely forget about Curitiba. It would just overwrite in your state. You would just overwrite the destination. And we formalized frame tracking to model the memory in the dialogue. So here we kind of keep track of everything that happened in the dialogue in separate states. So at the beginning we had Curitiba, and then when the user said, okay, what about if I go to Columbus? Then we created another state with Columbus in it. And the advantage of that is that then you can go back to Curitiba if the option in Columbus is not good enough, for instance, for the user, and he just wants to go to Curitiba, as in the dialogue that I just showed. Then you have the state still in your memory, and you don't need to ask the user again for all the information. You just remember it from the dialogue. So that's the task. That's kind of our way of modeling memory in a task-oriented dialogue system. And right now we're working on a model. I cut the part with the model because we haven't published it yet, so I just put the input and the output. So basically what it takes is the frames, so all the states that have been seen in the dialogue, so all the destination cities or budgets, etc. It takes the current user utterance, so here, for instance, anything better in Montreal, and it takes the NLU for this utterance. So here, inform that the destination city is Montreal and ask for a price. And then it for those dialogue acts extracted by the NLU, it will output in the end whether or not to which frame those dialogue acts are referring. So here it's referring to the frame number 2, for instance. In the output here we have inform ref equals 2. So that means that this utterance is referring to frame number 2 here, that we can see in the input that was budget equal $2230 and our destination city equal Montreal. So that's a model we're going to publish very soon. I need to finish, so that's good because that's the end. So those are the papers that I talked about during this talk. They're all online. You can find them on our website, maluuba.com. And as everybody else, we're hiring, so please visit our website or just shoot me an email at layla.lasri@microsoft.com, and thanks a lot.